I am not a plumber, don't learn from me, but this is part one of me installing Scotland's most powerful instantaneous electric shower. So I used an angle finder and loads of extension bits to drill through to where I wanted the shower drain. Then I made some teeth in a bit of pipe to finish it off. That worked surprisingly well. I had to move the shower drain flow out of the bathroom and into this wee utility room so that it can be pumped up to the wastewater heat recovery system to extract the heat out of it and give me that high flow rate I was after. I was trying my best to minimize the disruption to the insulation and to the air tightness. I used a bit of foam for the pump to sit on just to minimize vibrations, and then I used air tightness paint over every part of both of these holes. This wee setup here should more than double the flow rate of my electric shower in the bathroom using next to zero energy. This thing here is a wastewater heat recovery system. It's a simple but really powerful thing. So warm water, instead of just going straight into the drain, it gets pumped up through this pipe here and into the wastewater heat recovery system. It goes through this cyclone device here that spins the water around and then sends it down this drain pipe. The cold water comes in the bottom here and flows in the opposite direction in a different pipe surrounding the drain pipe. So the cold water comes up this column and steals as much heat as possible from that used shower water. And then this preheated water feeds the water heater. And the higher the temperature I can get that water, the higher flow rate will go through this water heater and the more powerful a shower I can have. You can see the complex plumbing that I've got set up for it. All kinds of different valves and directions that I can flow. This is mostly out of my own interest, but also so I can show people the different ways that you can tie this into a system. The next step is to test it. I'm hoping for 10 litres per minute. That's always been my target for the shower in the micro house, and that's about double the flow rate of a normal electric shower.
Okay, my shower works, so let's test it properly. The temperature you're seeing on the screen just now is the preheated water temperature. So that's the water that's run through the wastewater heat recovery system already. And you can infer from that the flow rate. The maths is quite easy and is fully predictable. So this is the flow rate that I'm getting out of the shower right now. But this feels like a powerful shower.
Okay, let's test it. So there's a few different ways that I can run things here. System A, B, and C. But for the purposes of testing, I'll use system A because it's supposed to be the most efficient one. I'm going to use this 2-litre jug to measure the flow. So I can feel that's hot now. Timer. 7.3. 7.3. 7.7. Made a bit of a mess here. Okay, so that was 7.3, 7.3 and 7.6 or something, but to be honest, this is the second time I've done this, and last time I did it I got 8 seconds, so let's be conservative and use that. 8 seconds equals 15 litres per minute. 15, it's a huge amount. Okay, I've got the whiteboard out. We're going to do some maths. Hopefully I don't bore you too much, but this stuff is important to this. So let's go through it. The specific heat capacity of water is 4184 joules per kilogram per Kelvin. So that's how much energy it takes to change the temperature of water. Cold water today is 10 degrees centigrade. That's measured. I have thermocouples and I have a thermal camera. And the shower water is 40 degrees. And that gives us a delta T of 30 Kelvin, because when you're talking differentials in temperature, Kelvin and Celsius are the same thing. Let's calculate the amount of energy required in 1 minute to take this shower water from 10 degrees to 40 degrees. So to do that, we take 4184 and we multiply out the kilograms and the kelvins. So we have 15 kilograms of water, because a kilogram and a litre are the same thing, or almost the same thing. And the kelvins change is 30. If we calculate that out, that gives us 1.883 mega megajoules. So that's the amount of energy that's getting provided to that water to change it in temperature from 10 degrees to 40 degrees. So now we have to think about, where does that energy come from? It's come from two places: the water heater and the wastewater heat recovery system. We don't know right now how much is coming from the wastewater heat recovery system, but we do know how much is coming from the water heater. My water heater is a 14 kilowatt water heater, and that's measured via CT clamp. That's confirmed that today is running at 14 kilowatts. So 14 kilowatts is 14,000 watts. And to get that into joules, we just need to multiply it by the number of seconds, 60 seconds, and that gives us 0.840 megajoules. So now we have the total energy in the system, we have the energy that comes from the heater, and now we can work out how much energy is getting given by the wastewater heat recovery system. Is the difference between those two: 1.043 megajoules. Now we have that, we can work out a couple of useful things. The first one is the efficiency. If you look at the documentation from the manufacturer, I should be getting an efficiency of somewhere around 55%, but let's work it out. So the wastewater heat recovery system energy, 1.043 divided by total 1.883 times 100 gives us 55.4%. So we're bang on where we're supposed to be as far as efficiency is concerned. But we can also work out what the effective power of the wastewater heat recovery system is. If we just divide this 1.043 megajoules by 60, we get power, and that is 17.4 kilowatts. A huge amount of energy is getting conserved by the wastewater heat recovery system. So 17.4 kilowatts of effective power being supplied by that wastewater heat recovery system. It's so much better than I thought it would be or hoped it would be. And it's giving us 15 litres per minute. And that is just amazing. And this could be Scotland's most powerful domestic instantaneous electric shower. A very niche thing, but it could be.